Hello students, today I want to talk to you about the periodic table of elements. Before we get started, let's appreciate one cool thing. When the table was designed in the mid-1800s, we did not have physical evidence of all of these elements. In the mid-1800s, we only knew about 63 elements. The first element that was discovered by science was phosphorus, discovered in the mid-1600s, and prior to that, humans understood that there were different metals and they behaved differently, but we didn't understand really what an element was or how they were organized or defined. And so since the mid-1800s, we've been characterizing the idea of elements on our planet in the periodic table. There is some debate as to who the father of the periodic table is. Could be Mendeleev, could be a German named Meyer, but the key thing is that's not important. Usually there are lots of human beings working on discovering the next interesting thing from the conclusion before in what we know is the scientific process. So there are many examples in science where in your textbook it says one person, quote unquote, discovered something or was the father of it, but really there were several scientists working on it, and that one person gets all the credit because they published first. And so when we talk about the scientific process and it being a cycle, the last piece after conclusion is to communicate that science to the community around you for feedback and review, and that leads to new observations. So people come to these things at the same time because we're all learning together and discovering together. So here we are in the periodic table. In each square, there's lots of information. Let's focus on the first important thing, which are these letters, 1 or 2 letter combinations. These are chemical symbols that define the element, and then the element name is written right below it, but not all the time. Sometimes more simplistic periodic tables don't show that. So what is an element? It's the fundamental units of matter on planet Earth, and one base unit of those fundamental elements is the atom. The atom itself has a proton and a neutron in its nucleus, and the electrons are infinitesimally farther away in the valence, and the electrons are the currency of chemical reactions. So right below this word iron, we see this funny phrase here, and this is kind of beyond where we're going in this introductory course. You also see this electron configuration block here, and you might recall something like this from high school, the Aufbau diagram, which describes how the electron valence shells are filled based on electronegativity. But we won't worry about that too much. We're going to talk about the pattern of electrons, but not worry too much about which orbitals they're in. Okay, so now let's look over here. We have an atomic number for a element, and we have a standard atomic weight, and that is measured in the units of atomic mass units. So what does all this mean? The atomic number relates to the number of protons, positively charged subatomic particles in the center of the element. And so we see hydrogen, it says 1. There's 1 proton. And then as we go over, you always read from left to right and down the rows to helium. This is the atomic number 2, 2 protons. But let's take a moment to appreciate standard atomic weight. So here in hydrogen, the atomic weight is 1.008. You can think of the 0.008 as being the insignificant mass of the really tiny electron, and 1 being the mass of 1 subatomic particle. But if hydrogen is 1, and I just told you that there's a neutron and a proton in the nucleus of every atom, of course, here presents our first exception to the rule. Hydrogen is an exceptionally small atom and it has no neutron. So, but when we go over here to helium, we see that its atomic number is 2 and its atomic mass is 4.0026. So 4 subatomic particles in the nucleus plus some minor addition of mass from the electrons. Okay, so now we've dissected the squares. We understand where we're going with this. And what I now want you to appreciate is who wants to bond with whom. So we will start over here because this is what you probably remember from high school as being the noble gases. Why are they noble? The idea here is that way over here in group 18, these elements don't want any electrons. So what do I mean by that? I already told you that electrons are the currency of chemical reactions. And so by currency, one of the designs of the periodic table is to confer information about how many electrons each element has and how many it wants, okay? So most electrons want their outer valence filled, and filling the outer valence gets back to this electron configuration thing. Let's look over here. Where are we? Oops. Basically, as they get new electrons, they fill them in the orbitals, and as a result, they become more stable, because if you have all the electrons you were hoping for, then you're not involved in chemical reactions which are designed to gain or lose electrons for more stability in electronegativity. And that brings me to this last number here, the electronegativity of the element. And as we look here, we're going to see that there are trends in this number. So for example, here, lithium is, where is it here? 0.98 and then 1.57, and then we go over 2.04, 2.55, 304, 344, 398, nothing. It's not electronegative at all. Neon, noble gases. So what does that mean? What trend did you notice in the numbers? I hope you noticed that the electronegativity gets greater as you go from left to right. So let's look at these group numbers. What does that mean about the group number and this electronegativity getting greater? So group 1 elements all have one electron hanging out in the outer position of their atomic structure. Okay, and then group 2 elements have 2 electrons. We're going to forget about 4 to 12. These are heavy elements that don't really interact in biological ways, except for, of course, some of these metals that we need in very small doses, and we call those vitamins. But we move over to 13, and here what I want you to realize is 3. So we went from 1 to 13. Now we have 3 electrons in the outer valence, 4, 5, 6, 7. And then we get to group 18. Here we have 8 possible electron spaces in outer valence and 8 filled spaces. So no electronegativity, okay? But now let's do some more periodic math. So the electronegativity, as we just determined, is related to how many electrons are in outer valence, okay? And if we look down the rows, we'd see that same trend of the numbers increasing as you go from left to right. So if there are 8 needed, simple periodic table math, if I asked you if a group 1 element, which elements would group 1 elements want to bond with to gain noble status and lose electronegativity, your math problem is 8 minus 1 equals 7. Group 17 elements often bond in a 1-to-1 ratio with group 1 elements. Okay, and then say there were we had group 2, and so now the math problem is 8 minus 2 is 6. So group 16 elements bond in a 1-to-1 ratio with group 2 elements. And then you can do math like this where you have a 1-to-2 ratio or a 3-to-1 ratio, but the basic gist is that elements are interacting with each other to gain this kind of nobility where there's no charge. All the electrons are balanced with the subatomic particles, the protons in the nucleus, and therefore the plus minus charging is balanced. And so simple periodic math matches the left side of the table with elements on the right side of the table. In the most generalistic conclusions, elements on the left side bond with elements on the right. Now, the last final thing I wanted to talk to you about was which ones are biologically important, okay? And these are going to be these top ones in the top few rows, okay? And take a look. You're familiar with these: hydrogen, water, carbon, okay? Phosphorus, nitrogen. These are extremely important elements central to almost all biological molecules, whether macromolecules that are nitrogenous make up DNA, nucleic acids, and uh, proteins, and then carbon-based carbon, oxygen, and hydrogen molecules without nitrogenous compounds make up our starches. And so we can see those connections there. Now, thinking about what vitamins and minerals are, take a look. Where are your vitamins and minerals on the table? So those are a little bit lower down, and you need them in fewer chemical reactions in your body, so you don't need abundant quantities of them. Your body is 70% water, so that means it is 70% hydrogen and oxygen. Then all of the structures of your body, every single biological molecule has carbon in it. That's what an organic molecule is. And so just take a moment to appreciate how many atoms of carbon there are in nitrogen. And phosphorus is the currency of ATP, the molecule that we use as energy inside of our biological cells. So look here, though, as we go down, selenium is vitamin, zinc, copper, iron, manganese. You may have taken any of these in multivitamin, potassium. But then as you get really down far in the periodic table, what I want you to appreciate is, look, these elements have massive nuclei, okay? They have really huge amounts of subatomic particles, and their electronegativity is immense compared to molecules or to atoms up at the top of the periodic table. Therefore, we find our radioactive elements, and these very heavy elements at the bottom of the table are dangerous to biological molecules. They're so heavy, they're like really heavy magnets, and they rip apart your biological molecules because that electronegativity is so high. So that's why, when we get into thinking about environmental contaminants, like here's lead, we're gonna think about these elements that are heavy down here and how they're stronger magnets that interfere with the biological reactions that keep us going every single day. I hope this was helpful.